Okay, so we've got the 1,000. It's just hooked up through the probe here, the positive and the ground. 1,000 hertz. So there are some cursors, and let's go to amplitude. Now, if you want any of these side functions, these are the buttons to access it. You can see here. So if we put the cursor on to measure the amplitude, what does it read? Can you probably can't see it. It's 1.00 volts on the top and minus 1.00 volts on the bottom. Well, what is this saying? It's 1 volt peak. So it's true to what it's saying. It's 1 volt above and 1 volt below. Did I put I think I meant to, but it's okay. I meant to put an RMS just for you to calculate the RMS value of who knows what it would be. If it's 1 volt peak to peak, what's the RMS value? Y'all aren't paying attention to my videos. It would be 0.707. It's the peak voltage over the square root of 2. And the square root of 2 is 1.414. The inverse of 1.414. Hello, 12, 24. We'll put one. Well, we'll do it the correct way. We'll do 2 square root is 1.414, and take the inverse is 0.707. So the RMS value would be 0.707 of this. Okay, now let's do the time. Well, I guess it's not automatic. Let's do it 0 crossing to 0 crossing. Okay, it's a little hard to tell, but one of these is solid and one of them is dashed. And so the solid line is the one that we're moving. I think, is there a, no, it didn't. How do you get coarse in? There's the 0 crossing. You can see the crosshair is right on that, or pretty close, right on that line. Now let's go to the other one. It's solid. Now I'm moving it. And that's pretty close right there. And the time, where is it reading it? Time. I guess it's delta T is 1.5 milliseconds. Is that correct? If it's 1,000 hertz, that should be 1 millisecond. Why is it showing us 1.5 from here to here? 1000. Let's do it from peak to peak. And what I'm looking for here, we'll put it right in the center of that peak. Push the button again, that makes the other one solid. Oh, you know what? I had it at the wrong zero crossing. So it was right. And there the delta T is I've got 1.01 seconds. Okay, I had this zero crossing and this zero crossing. That's why I said 1.5 milliseconds. Let's do that again. Let's reset this one. I even warned you about that in the one of the lectures, one of the video lectures, is be sure to use the same zero crossing. And I failed to do what I told you in the videos. Okay, here we go. Zero crossing to zero crossing, and the delta T is 1.0 milliseconds. So that's the period. The period is 1.0 milliseconds, which agrees with what 1,000 hertz should be. So both of these are reading pretty well. Okay, now let's try. The next one is the square wave. So we're going to go to the waveform and choose square wave. Oops, waveform, square wave. And there you can see no longer is it sine, now it's a square wave, right? And the cursor is still at 1.00 milliseconds, which is 1,000 hertz. That's correct. Now let's do the amplitude. The amplitude shows 1 volt above and 1 volt below. Now I don't know what the RMS of a square wave is, because it would be different because it's not a sine wave, but it's Christina, can you see what's going on? Oh, okay, you can see it there. Good. Okay, so that it's all working the way it should. Now let's change the waveform to triangle. And you can see it's a triangular wave. And that's the amplitude, once again, shows 1 volt. And if we do the time, it's still, the cursor is there at the crossing and there at the crossing, and it shows 1.00 milliseconds. Okay, so everything's fine. Let's go back to a sine wave, and I'm just gonna pick actually, let me do it. Okay, I just put in just kind of a random frequency, 1846. It says on on the readout. Can you read that on there? 1846. Yeah, you can see it on the screen. 1846. And I'm just going to put in a different voltage. 1.34 is what I have. Now, let's use the same measurement techniques. So let's go, we're at the time, so let's pick a upgoing. Actually, let's expand that. There, that's pretty good. So, okay, this is the I thought there was a cursor. Oh no, we want the cursor. I thought there was a way to do it. Oh, there it is. If you hold it, it's fine. And if you okay, now we go to this other cursor. And right now it's moving very finely. Let's push and hold it. And now it's coarse. So we want the upgoing um, zero crossing. Now let's do back there, but let's push and hold, and that should do a fine cursor, and it does. Okay, zero crossing to zero crossing. If that's T1, or you know, I want delta T. Delta T is 542 microseconds. Does it give the yeah, it says it right there, 1.846 kilohertz on that little that readout right there. That one says 1.846 kilohertz, which is exactly what I dialed in. So both of these seem to be pretty reliable. The old function generators we had were very, very sloppy. I like these new ones. And let's just check the time, 542 microseconds, 542, enter e to the minus 6. Oops, I messed up. All right. 542 e to the 6 minus 18,450 is what I got on the with the cursors. But that's my adjustment. That was my going back and forth. It's reading it correctly, 1846. Okay, what else am I asking for on there? Okay, let's go on to oops, square wave. And let me adjust. This one might be hard to adjust. It's such a fast slope. 542. This still says 1846, so that's good. What did I add? Okay. The period on this is 542 as best as we can measure it on here. And the amplitude oh, it didn't do that automatically. It adjusted. 1.3 volts and minus 1.3 volts. And what's it set at? 1.3 volt, 1.34. So it's a little bit off. Everybody getting the cells filled out the way? Okay. Now, let me go on to sawtooth. Oops. Or not sawtooth, triangle. Okay, this one says that's a little on the top. It says 1.32 and 1.28. So it's probably just the way I've got the cursors positioned. But let's do the time. It's the same zero crossing. It still has 1.846 here, and it's still 542 microseconds for the period. Okay, now that takes care of the first part. Now, let's get our protoboard. Take this out. Flip lights flat. I've got a 1000. It's brown, black, red. Brown, black, red. So that's 1000. And now I'm putting the how do we want to do this? Going through the resistor, from the resistor to the this solenoid here. And from the solenoid which is it is an inductor. From the solenoid to this, and back. So we follow this. It's coming out of the signal generator into the resistor, into the coil, and back to the generator. Now we want a sine wave. And we want to look I want to look across the resistor. Okay, looks pretty sloppy, doesn't it? Let's now we're back at 1001 volt, but the frequency oh, you know what I want? I want square wave. I want a square wave. There we go. I wonder if I had this across the inductor. Oh, that's a lot cleaner. Okay, let's look at cursor, and let's do the amplitude. Let's put this one at the peak. And it's 1.5 volts, 1.52 volts. Um, 1.52 volts peak. So 0.37 is 56.25. Let me do that again. 1.52, 1.52, enter. 0.37 times 56. So 0.56. Let's move the 0.56 right there. So now let's get, well, gosh, I thought it would stay. Okay. Let's do the amplitude again. 0.56 is just above, there's some dotted lines there, and just above that is the 0.56. I moved the wrong one. A little bit lower. Oh, that's coarse. Not fine. I'm gonna estimate it's about right there. That's the 37% point. So now, if we look at that delta, the delta T, it's 11.2 microseconds. 11.2 microseconds. I should be writing this. So now we know that this is 1,000 ohms. And how do you get the time constant for an LR circuit? It's L over R. It's L divided by R. That's for the resonant frequency. This is just for a LR time constant. So if tau equals L over R, L equals tau times R. So 11.2 microseconds times 1,000 ohms that would be, well, just 11.2 millihenries. Yeah, 11.2 millihenries. Okay. Now, is that all the parts of that you need to answer on that section?